Welcome to the world of queuing theory. This is the mathematics of customer service and traffic flow. In this video, we're going to explore the fundamental concepts of queuing theory, which is essential for understanding and optimizing waiting lines in various real-world scenarios. So, what exactly is a queue system? It is a mathematical model used for analyzing waiting lines. In a queue system, customers or entities arrive, wait in a line for service, and are then served by one or more servers. Think of it like this: people arriving at a bank, waiting in a line, and then being served by a teller. Queue systems are everywhere. Some common examples include bank lines, traffic lights, computer systems processing tasks, and call centers handling customer inquiries. Understanding queue systems helps us manage and improve efficiency in these processes. Every queue system consists of 4 key components. The first is the arrival process. This refers to the rate at which customers or entities enter the system, and it's often denoted by the Greek letter lambda. Next, we have the service process. This represents the rate at which customers are served, and it's typically denoted by the Greek letter mu. Then, there are service channels, which indicate the number of servers available to provide service. This can be a single server or multiple servers working in parallel. Finally, we have the queue discipline, which defines the order in which customers are served. Common queue disciplines include first in, first out or FIFO, last in, first out or LIFO, and priority-based service. To describe and classify queuing systems, we use Kendall Notation, which is a standardized format for representing the characteristics of a queuing system. The basic format is a /s/c. A represents the arrival process, indicating the distribution of inter-arrival times, such as Markovian, deterministic, or general. S represents the service process, indicating the distribution of service times, also like Markovian, deterministic, or general. C represents the number of servers, indicating the number of service channels available in the system, such as 1, 2, 3, and so on. Let's dive into the basic M/M/1 queue model. This is a fundamental queuing model that assumes a single server queue with Poisson arrivals and exponential service times. Key characteristics include a Markovian arrival process, meaning that arrivals occur randomly and independently. A Markovian service process, meaning that service times also follow an exponential distribution. A single server, indicating that there's only one server providing service. An infinite queue capacity, meaning that there's no limit to the number of customers that can wait in the queue. A crucial concept in queuing theory is traffic intensity, denoted by the Greek letter rho, which is calculated as lambda divided by mu. For the queue to be stable, meaning that it doesn't grow indefinitely, rho must be less than 1. To evaluate the performance of a queuing system, we use several key metrics. L represents the average queue length, which is the expected number of customers in the system, both waiting and being served. L subscript Q represents the average queue length waiting, which is the expected number of customers waiting in line. W represents the average wait time, which is the expected time a customer spends in the system, including both waiting and service. W subscript Q represents the average queue wait time, which is the expected time a customer spends waiting in line before receiving service. Now let's look at some important formulas for the M/M/1 queue model. The average queue length L subscript Q is calculated as rho squared divided by 1 minus rho. The average system length L is calculated as rho divided by 1 minus rho. The average wait time W subscript Q is calculated as rho divided by mu multiplied by 1 minus rho. And the average system time W is calculated as 1 divided by mu minus lambda. Queuing theory has numerous real-world applications across various industries. In banking, it's used to optimize customer service lines and teller staffing. In traffic systems, it's applied to traffic light timing and intersection design to minimize congestion. In computer systems, It's utilized for CPU scheduling and network packet processing to improve system performance. In call centers, it helps with agent staffing and response time optimization to enhance customer satisfaction. In healthcare, it's used for emergency room management and appointment scheduling to improve patient care. And in manufacturing, it's applied to production line efficiency and inventory management to streamline operations. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.